Welcome to this lecture. In the last lecture, we had seen some of the main requirements for a real time operating system, and then we are trying to understand why the traditional operating systems do not support those features and what needs to be done to support those features. And with this intention, we are trying to dissect the Unix operating system and find why it does certain things and how it can be improved. Let us look at using Unix as a real time operating system. For all the features that we discussed in the last lecture that a real time operating system needs to support, those are not satisfactorily supported by Unix. But then there are two issues that are the major obstacles in using Unix in a hard real time application. The first is non-preemptable kernel. When the Unix code is being executed, that is the kernel code is being executed, then all interrupts are disabled. And the second issue is the dynamic priority levels. The Unix operating system keeps on shifting the priority level of a task at every time slice. Now, let us try to examine why it does this. First of all, why does it disable all interrupts when executing kernel routines, and also why does it have to keep on shifting the priority of a task? Because in this situation it becomes difficult to run a real time scheduler like rate monotonic scheduler, because the scheduler works on the assumption that the programmer assigned priorities do not change. First, let us look at the non-preemptable kernel. A preemptable kernel is also called as reentrant kernel, that is once an interrupt occurs, then the kernel routine stops after the interrupt, and then again after some time it continues from that same place. That is a reentrant kernel, can be interrupted. But then the Unix is a non-reentrant or a non-preemptable kernel. To achieve this, all interrupts are disabled, so that the kernel cannot be preempted and it runs all the code that needs to be done. But then you will have question that why is it not reentrant? Can't it be interrupted? Some other code runs and then starts running the kernel code where it left. The answer is no, because that will destroy the integrity of the kernel data structures. The developers of the Unix, to make the operating system efficient, did not use kernel level locks. So, if a data structure is part of the operating system that is modified halfway, and then there is a preemption and some other part the operating system runs and then modifies this data, inconsistent data it reads or modifies, then it will lead to an inconsistent system and can crash the system. But then to make the problem more severe, the user tasks can also run in kernel mode. We will see this issue, but let us just understand this point that the traditional operating systems such as Windows, Unix, etc., the kernel is non-preemptable. The main reason is that it is an efficient way to preserve the integrity of the kernel data structure. Of course, we are talking of Unix 5 and then the later versions of Unix and the Windows and the Linux, they did make the kernel preemptable. Please note that we are discussing here the Unix system 5 as it is, but later developments, because this was a big handicap having a non-preemptable kernel, and the main reason is that there was no kernel level locks were used, and therefore, disabling interrupts was a efficient way to preserve the integrity of the kernel data structure, but this is a big handicap, and therefore, later versions of the Windows and the Unix, they did make the kernel preemptable through use of kernel level locks. But if the kernel is non-preemptable, then it can cause deadline misses, because the task preemption time becomes the time spent in the kernel mode plus the context switch time, and the time spent in kernel mode can be of the order of a second in the worst case, because typically the context switch time is set as 1 second, and the kernel routine can run up to a second, and if a task, high priority task, is prevented from running for 1 second, then definitely it will miss deadline, because typical deadlines are of hundreds of microseconds. To make the matter worse, even a user program can execute in kernel mode. When a user program makes a system call, it runs in kernel mode, generates a software interrupt, changes the mode to kernel mode, and therefore, even when a user program is running and makes a system call, it becomes non-preemptable. The original Unix developers wanted an efficient operating system, and they did not visualize the use of Unix in real time and multiprocessor applications. Now, let us look at the second issue, which is the dynamic priority levels. If we look at the Unix scheduler, it uses a multi-level feedback queue. It divides the tasks into several priority ranges, and for each range it maintains a separate queue. The different priority ranges are the user levels. So, there are n user levels, maybe 256 user levels. Then kernel processes are higher priority than the user processes. The user processes cannot really migrate to kernel level, and there are several other bands of priority. The files, buffer, disk IO, and the swapper is the highest priority in the Unix operating system. And the system by default uses a 1 second time slice, and the tasks, after they complete their time slice, the user tasks, once they complete their time slice, the priorities are recomputed. If you look at the traditional operating system book, you will find that the priority of a Unix task at its jth time slice is computed at its base priority, a nice value, and the CPU uses time, it is a history of CPU uses time. The history of CPU uses time is given in the form of a recurrence relation. The CPU uses time at j is half of utilization in the j minus 1. So, 50% weightage to how much utilization of the CPU occurred in the previous time slice, and the rest half is the history of CPU uses previous to the j minus 1 instant. The priority Tij is the priority of the task Ti at the jth instant, of uses time slice. CPU Tij is the history of CPU uses, geometrically decreasing weights for the CPU uses, and the UTij is the CPU utilization at the jth instance. Base Tij is a value used by the operating system to separate different tasks into priority bands, and nice Tij is set by the programmer, and as indicated by the name nice, a programmer can only reduce the priority of his task, cannot really increase the priority. Now, let us look at this term CPU Tij. CPU Tij is given in the form of a recurrence, that is CPU Tij minus 1, half of the weightage is given to the history of CPU uses over instance j minus 1 and earlier, and half the weightage come from the last time slice that it obtained, how much it has used the CPU. If we unfold this recurrence, we see a geometrically decreasing weightage to the utilization over the different time instances. The last time instance is given 50%, the in time slice before that 25%, 12.5% and so on. So, this is a geometrically reduced weightage for past CPU utilization history, but then you might be wondering that why does it have to do so. Before we answer that, let us look at another thing, is the base priorities. The entire priority band is developed, is split into different priority bands: swapper, block IO, file manipulation, character IO, kernel process, and the lowest are the user processes, and the user processes cannot migrate to other priority levels, and also a task at a certain priority level cannot cross its band. The central idea here is that the IO is a bottleneck. CPU executes at high speed, the IO takes time, and therefore, if a task needs to do its IO, then its priority must be high, otherwise the response time will be low. The IO channels need to be kept busy as possible. If a task is doing its IO, it is in the IO phase, its priority should be enhanced, so that all the IO requests are raised and the IO channel is kept busy. And that is the reason why IO bound tasks, the priority is made higher and higher, whereas CPU bound tasks, the priority is made lower and lower by use of the priority scheduling formula, the priority computation formula which we just looked at. To increase the average throughput, the priority of the IO intensive tasks need to be raised, and therefore, the utilization of the CPU in the previous instance is computed, and if the utilization is low, that indicates that it is doing IO, then the priority of the task increases. Remember that in Unix, the lower is the priority value, the higher is the priority, and therefore, if the utilization is low, the priority increases. The IO bound processes gravitate to higher and higher priorities, but if we are trying to use such a operating system in real time situation and the critical task is doing its processing using CPU heavily, then its priority will keep on decreasing and it can miss deadline, and this becomes unacceptable in hard real time applications. So, we just saw two major problems of Unix: non-preemptable kernel and dynamic priority levels. So, the Unix with its dynamic priority level and its non-preemptable kernel can only be used in soft real time applications. It is not suitable for hard real time applications where the deadline is of the order of milli or microseconds. If we recapture, the main deficiencies of Unix 5 are task preemption time of the order of a second, dynamic recomputation of priorities, resource sharing protocols are not supported, inefficient interrupt processing, unsatisfactory support for device interfacing, like you add a new sensor, you want to incorporate a new sensor or a actuator device, and then you need to recompile the operating system, stop all tasks, shut down the system, etc. That is not acceptable in a safety critical hard real time situation. You should be able to do it when the system is operational. Support for timers is unsatisfactory and lack of real time file support. These are main deficiencies of the Unix 5 if we want to use it for real time applications. Now, let us look at one last issue before we conclude this course is POSIX. If we look at the origin of POSIX, it had to arise because Unix, once it was developed by AT&T, it gave it free to many recipients. Whoever wanted the Unix code, it was distributed by AT&T. Because AT&T was after all a telecom company, and then that point of time it did not have interest in developing operating system, and those who received it, they extended in various ways, IBM into AIX, HP into HPUX, Sun into Solaris, the Digital Corporation into Alteryx, and so on. Even though the Unix code was developed at AT&T, it was extended in various ways by different vendors, and the result is that Unix code became incompatible. If you run an application, you write an application on one platform, it will not run on another platform, because the syntax and the service semantics differed. The different Unix version offered different services. So, you develop code on one version, it will not work on another version. To make the code compatible at the source code level, the POSIX was attempted, stands for Portable Operating System. You might wonder that it comes to POS, but what about IX? The IX was simply suffixed to POS, the Portable Operating System, to make it look like Unix standard. But then it became so popular that even the non-Unix operating system also became compatible to the POSIX, and therefore, the POSIX has been a huge success. The major concern for POSIX is portability of applications written in different operating systems. Now, POSIX is widely accepted. Even non-Unix operating systems use the POSIX standard. The POSIX has been accepted as an international standard. The IEEE P1003, the ISO standard 9943, etc., they recognize POSIX as a standard. If we look at the POSIX, the standard document, we will find that it defines only what should be the operating system calls or the interfaces to the operating system, and what should happen once the calls are made, that is called as the semantics of the call. But it does not tell how the operating system calls are to be implemented. It just says that what parameters it needs to take, what should be name of the calls, and what it should achieve, but how exactly to be written, it does not tell about that. If we look at the POSIX, there are several volumes of documents. One is POSIX 1, which deals with system interface, that is what are the system routines and what are their parameters and the semantics what it does. POSIX 2 on the cells and the utilities. POSIX 3, how you can test whether a operating system is POSIX compliant, and the fourth document deals with real time extensions, the POSIX RT. Now, let us look at the real time POSIX. It requires an operating system to support certain features, then only it will become RT POSIX compliant. The first one of course is preemptive priority based scheduling, and it defines some performance metrics which the operating system must satisfy, that is the worst case bound on the execution time of various system calls. It requires support for static priorities. We had seen that the traditional operating system did not support static priorities, but now many of the traditional operating systems also support static priorities. It requires that at least 32 priority levels must be supported, both absolute and relative timers must be supported, nano sleep function to provide high precision timers. In the virtual memory, mlock, that is lock a page, mlock all to lock the entire address space, memory unlock, that is to unlock a page, and so on must be supported. Multi-threading support, real time file system support for supporting pre-allocated and contiguous files must be supported. So, we just right now saw some issues if we want to use the traditional operating systems in real time applications. We looked at Unix, and then we looked at what problems may occur if Unix is used as a real time operating system, and then we looked at a standard, the POSIX real time standard, which all real time operating systems must support. We looked at major requirements of the standard, and one of the requirement is static priority levels, 32 priority levels. The scheduler should be implementable using preemptable priority based scheduling. We are almost at the end of the course. Now, let us do a few practice questions before we complete the course. This is already we have discussed, but then just to check whether you have really followed the course. One of the crucial issue that arises when tasks share resources and we do not have adequate support for resource sharing is the priority inversion problem. What do you understand by the priority inversion problem? How does it arise, and what are the solutions of this problem? Please go through the lecture material and try to answer this question, that what is the priority inversion, the unbounded priority inversion, and solution to this problem. Now, let us move to the next question. When several tasks share a set of critical resources, is it possible to avoid priority inversion altogether? Can we really make priority inversion 0, number of priority inversion 0, when we have tasks that share resources by using any protocol, any resource sharing protocol, maybe priority ceiling protocol, maybe highest locker, or the simple inheritance based protocol? The answer to this question is no, because if a low priority task is holding the resource, then the high priority task has to wait. and therefore, at least one priority inversion must occur, and it is not possible whatever be the priority, whatever may be the resource sharing protocol that we use, it is not possible to avoid priority inversions altogether. Now, let us look at further questions before we conclude this course. You can ask specific questions. For example, what do you mean by inheritance related inversion when using a priority inheritance scheme, maybe a priority ceiling protocol? What do you understand by inheritance related inversion? Give an example of a inheritance related inversion. When a set of real time tasks share certain critical resources using the priority inheritance protocol, is it true that the highest priority task does not suffer any inversions? Let me repeat the question again. If we have a set of real time tasks that share critical resources and they are using the priority inheritance protocol, is it true that the highest priority task does not suffer any inversions? The answer is false. If we said the lowest priority task does not suffer any inversions, that would be true, but the highest priority task would suffer inversion when a low priority task is already holding a resource and the high priority task becomes enabled. With this, we will conclude this course. We just looked at some basic aspects of real time operating systems. We saw how a real time operating system differs from a non real time operating system. We considered real time task scheduling as the central problem that a real time operating system needs to handle, and we discussed the important task scheduling algorithm. We looked at analysis of tasks to see whether they can be scheduled on a processor, looked at resource sharing issues, and then we looked at multiprocessor scheduling, and then finally, we have been looking at some issues that a real time operating system needs to support. The traditional operating systems lack support for that. We investigated why it was so, and then we explained or offered some solutions for that, which all real time operating systems they do follow those.